Hello and welcome. We're doing section 6 in the carbohydrate chapter of the Klein textbook, and we're going to be talking about reactions of monosaccharides. Now, since this is a video, I have a little bit more luxury to go into the mechanism for these different reactions. So if you're just interested in a reaction in particular, maybe just what happens or what the products are, or even maybe the mechanism, check the timestamp in the description of this video below and just go ahead and jump to the reactions that are needed, okay? The textbook is quite scant on some of these things and it's quite elaborate on others, so I just want to be thorough as possible. All right, the first reaction we're going to talk about is acetylation. And we know that alcohols will react with acetic anhydride to make acetates or acetate esters. We know the synthesis of aspirin involves taking a phenol, treating it with acetic anhydride, and it makes the acetate of that phenol derivative. So let's talk about acetylation. Let's take a typical sugar here. All right, and this is basically an alcohol. You can think of this as an alcohol. And if we treat this with excess acetic anhydride, in the presence of pyridine, we will get per-acetylation. That means we'll get an acetylation on every single one of these hydroxyl groups. The hemiacetal hydroxyl group, the secondary hydroxyl groups, and even the primary hydroxyl group, okay? So we'll get this as a result. And we abbreviate, rather than, I'll draw one of them here, okay? So this is the acetate, all right? And we abbreviate acetate AC, okay? So this right here is acetate, and it's abbreviated with the letters capital A, small c. So to make it more simple to draw, we just write OAC on all of these guys, okay? Now, the book doesn't mention this. They just say, oh yeah, see the previous chapter. But I just want to take you through the mechanism in case you're kind of worried or you want to know how that mechanism works, okay? So here we have our alcohol, all right? This is going to happen, 5 times, but I'm just going to show one of the mechanisms, all right? We have our alcohol. We have acetic anhydride, okay? And the alcohol is going to attack either of the 2 carbonyls, okay? And you make the famous tetrahedral intermediate here. I'll just label that C. All right, so you have O minus, okay? You have acetate in this direction. And down here you have a methyl group, okay? I'll just make it CH3 so you can kind of see that all forming there, okay? Now this alcohol brings in that hydrogen with it, so don't just leave it off because it's convenient, all right? So in this step we have attack occurring, all right? And this is found in chapter 21, I believe. The carboxylic acid derivatives react by nucleophilic acyl substitution. So now we want to kick off our leaving group. Acetate is the leaving group here. So we have a negative charge, okay? And we're going to form the carbonyl of our acetate, and we kick off acetate, all right? So this is the elimination step because we're basically eliminating acetate. I'll just put minus OAC now that we're familiar with the abbreviation for the acetate group. There's a negative charge on the oxygen, right? So that's called acetate ion. So we get the intermediate here. It's almost the ester, okay? We just have this proton here that we need to remove. Okay, so we've got our acetate on there, and now this is where pyridine comes in. So remember that pyridine is a heteroaromatic amine, okay? And the lone pairs here are basic. So we can use pyridine as a base to remove this proton here, okay? And that's going to give us the ester. So that step is a deprotonation step. And let's draw the product, ROAC, okay? So those are the steps there, all right? Reaction number 2 is alkylation, okay? And we're making an ether, okay? So the reaction, once again, we'll draw this molecule, typical sugar. Okay. And we're going to do an SN2 reaction with methyl iodide. Okay, we're going to add excess methyl iodide, okay? And then we need a base present to deprotonate the hydroxyl group so that they're stronger nucleophiles and will attack the methyl group and kick off the iodide, as you know from the Williamson ether synthesis, okay? We can't use a strong base for reasons that might be discussed in the textbook later on. It decomposes the sugar. So we use a milder base, okay? And I'll just make note of it here. You need to use this base. You can't use sodium hydroxide or something like that. It'll chew up your molecule and it will ring open and other things will happen that you don't like, okay? So this is just a weak base, okay? And what you get here is a methyl group on every single oxygen. So you make a methyl ether, okay? So let me draw the product here. So there's the methyl ether. The methyl ether here as well, okay? All of the alcohols become methyl ethers, okay? What is the mechanism for this? Well, let's just draw what happens here. So you have your alcohol, okay? And then a weak base comes in. I'm just going to write B. We don't need to really worry about silver oxide and the structure of that. Base is going to come in, okay? And that's going to form your alkoxide, okay? And then, so that's the deprotonation step. And this is going to attack methyl iodide, okay? All right. Another possibility is that your alcohol, since methyl iodide is so reactive, okay, can directly attack methyl iodide to give you this guy here, okay, and iodide. And then your base, which is weak, is your all right, so those are two different possibilities, okay? But it's an SN2 reaction, all right? All the stereochemistry of all of those hydroxyl groups is maintained because you're attacking this carbon. That carbon, the methyl group, is not a stereo center, so we don't need to worry about the R or S of that methyl group. You just put the methyl group on, okay? None of the alpha carbons on any of these hydroxyl groups gets inverted or anything during this chemical reaction, okay? Another way to form an ether, okay, is through the hemiacetal chemistry, okay? So this is another way. I'm just going to use methyl because it's just easy to draw, but we can take this guy here. And if we treat this with methyl alcohol and acid catalyst, now we could use anything. It could be ethanol or isopropanol or butanol or something like that. Okay, so keep in mind it could be different. But this is going to make the acetal, okay? So I want to make 2 points here. Point number one, well, so this is called the hemiacetal, and this is called the acetal, okay? I think we learned this in chapter 19 or 20, I don't remember the chapter number of the Klein textbook. But you can convert the hemiacetal all the way to the acetal by adding additional acid and an equivalent of alcohol to replace that hydroxyl group, okay? This reaction occurs by SN1. This means that you can have attack of the methanol from the top face or the bottom face of the resonance stabilized carbocation to give you the R or the S, okay? So these two molecules are isomers, right? This is the beta isomer and this is the alpha isomer. So this is going to give you mixtures of alpha and beta. Now recall what we called these in the stereochemistry chapter. These are called epimers. Every single stereogenic center in these two isomers are exactly the same, but the only difference is this stereogenic center. So if your whole molecule has a bunch of stereocenters and differs only by one, we call those epimers. Epimers, so the alpha and the beta isomers are epimers, okay? The other thing I want to mention is that we're, of course, talking about the hemiacetal carbon and the acetal carbon. Okay, so I'm going to dot it up here. Here's the hemiacetal carbon. Here's the acetal carbon. Only that carbon reacts in this reaction. Okay. Okay. Only the hemiacetal carbon hydroxyl group reacts. All right. So let me take you through the mechanism. This is greatly described in the book. So let's draw our little sugar out here, okay? And this is treated with acid, and we're going to protonate any one of these oxygen atoms, okay? And yes, the wrong one, the right one are going to get protonated as well, but it's very fast, it's in equilibrium. Eventually, the proton is going to be delivered to this hydroxyl group, okay? So it's not like, oh, how does that proton know to do that? You just have to remember that it can go anywhere. You can draw all these different possibilities, but this is the one that leads to the product, okay? So in the first step, as usual, when you have H plus in your reaction mechanism, use it in the first step of your mechanism, and we're going to protonate that hydroxyl group. Remember that the purpose of doing this is to convert that guy into a good leaving group. Neutral water is a good leaving group, okay? Next, we want to eliminate the hydroxyl group. As usual, always use your lone pairs if you have something next door to assist with the departure of that leaving group, okay? So in this step, we lose water. I'll just write it down on the bottom of the arrow. And you form a resonance stabilized carbocation. So this is the major contributor. I don't even see the carbocation, do you? This is the major contributor because every atom has an octet. That is the primary importance when you're ranking contributors towards the overall resonance structure, okay? If everything has an octet, it's great. That's going to be the more major contributor to the overall resonance average that you get, okay? We can draw another resonance structure, and I want to avoid uses of curved arrows for this because you'll see why in a second. I don't want to recopy all of this stuff. But if the electrons are pushed up towards the oxygen instead, we'll have a positive charge on this carbon right here, okay? So that's what I'm referring to as the carbocation. And that structure that I'm drawing here right now is the minor contributor to the overall resonance hybrid because carbocations do not have an octet. So they're much, much, much less stable if we were to analyze the bonding situation, okay? So this is the minor contributor. Now, since this is a resonance stabilized carbocation, this intermediate is quite stable, okay? It's reasonable, okay? It's very easily produced. Now, what needs to happen here is that methanol needs to attack. You can attack either one of these carbocations. It doesn't matter, okay? So in order for me to show the beta isomer, I'm going to attack from the top face. And that's going to give me the OCH3 pointing up. And then my hydrogen is going to be down, okay? And we've got all these, OHs here that are the same. All right? And then, of course, something's going to come in and deprotonate it. What's going to deprotonate? Methyl alcohol, for example, can be a nice general acid base to come in and deprotonate that, okay? So again, we have H plus in the reaction mechanism. We have methanol. We don't have hydroxide. Do not use OH minus or CH3O minus to deprotonate this. Under acidic conditions, you're only going to have neutral alcohols as your strongest base. So that's going to make the target molecule here, and that's going to make the beta isomer. Okay? Beta means going up. I'll not draw that hydrogen pointing down. All right, so we got all of these OHs here, and we're done. We don't need to draw anything else there. That's the beta isomer. Okay? Now, this methanol can attack from the bottom. So what if instead of that, I use my methanol molecule, okay, to attack the bottom side of this carbocation, which is planar, right? It's planar, so it can attack the bottom lobe of the p orbital there, and that can give me the alpha isomer after I draw it all out. So let me draw the intermediate here. Okay, so there's my protonated acetal, and I've got all of my hydroxyl groups. Okay, and then we have methanol come in and deprotonate. And this is going to give me the neutral ketal, and we call this the alpha isomer, okay? I'll draw it in yellow here. So I know it takes a while to draw out, and maybe even you're skipping this part of the video, which is fine. I just want to help somebody who might be lost. Now, the exact ratio of these are going to depend on the sugar that you're using, but you normally get most of the alpha isomer, okay, the major product is going to be the alpha isomer, and the minor product is going to be the beta isomer. So let me write that down. Okay, so this is the major, and this is the minor. Okay. All right, so that's how you make methyl ethers. Okay. Next up, we have reaction 4, epimerization. Okay, let's draw a sugar here using the Fischer projections now. And let's just show an aldose, okay? Now, if you treat this guy here with sodium hydroxide, we mentioned before, why do you use that silver oxide thing as a weak base? Well, here's the reason why. If you treat an aldose with sodium hydroxide, which is quite strong, you can actually epimerize this carbon right here, okay? So epimerize is the process of making two different epimers. And I mentioned before in the previous little clip there that epimers are two diastereomers. They differ by only one stereocenter. Okay, and this is a key term. All right, you should memorize these terms. They should not be foreign while you read the textbook. If we treat this with sodium hydroxide, so again, we're starting with one molecule. You know, you could think about an Avogadro's number of these, or we can just put a 1 here. Okay, so one of these molecules. Well, let's just do 2. Some students are a little worried about the half number. So let's say we start with 2 molecules of this. Okay, and we treat this with sodium hydroxide in water. Okay, and we will get 2 molecules being produced here, okay? We will get the original molecule back again, okay? And we'll form one of those, okay? And we'll form one of these, okay? Now, I apologize, it's not going to be 50-50 mixture. This exact ratio is going to depend on the stability of the sugar and stuff like that. So maybe I should erase the coefficients here. But I do want to make sure that you understand there is conservation of mass, okay? If you start with 10 molecules, you might end up with 6 molecules of one and then 5 molecules of the other, okay? So these are not racemic, they're not enantiomers, so they're not going to be in equal amounts, okay? It's not going to be a 50-50 mixture. So maybe it's best if I just make a note of that, okay? So it's not a 50-50 mixture necessarily because remember, diastereomers have different energies. How does this work? Let me show you the mechanism. If you don't need to see it, that's fine. The textbook is lacking on this. They say, oh, just remember how this works and you probably can figure it out. I don't think so. So I'm going to show you how it works, okay? So let me position my hydroxyl groups here. And the main point to notice here is that this carbon right here is the alpha carbon. It's adjacent to the carbonyl. And that's the key point to realize. That is the stereogenic center that's going to become epimerized in this chemical reaction. So we have hydroxide, okay? And we can draw the acid-base reaction like so. It's kind of weird to draw it like this, but I'll just draw a negative charge there on that carbon. And another way to draw this enolate, right? This is an enolate, is with the negative charge on the actual carbon atom, the oxygen atom. So draw the electrons moving up this way, and this is resonance, okay? And we can draw it like this. So let me just point to the alpha carbon in each one of these. So this is still the alpha carbon, right? And this right here is the alpha carbon, okay? And you can see how the alpha carbon has lost its stereochemical information. The alpha carbon is not a stereocenter. There's an alkene to that. So what we say is that it's planar, right? So the H plus can come in. The water can protonate this guy here from either the top face or the bottom face, okay? So here's my enolate, okay? And I'm going to pick up the proton from the left, okay? And that's going to give me the same molecule back again. All right. So I think that's easy to understand. Okay. These are, of course, all in equilibrium with one another. I'm going to redraw this on the next page, and we're going to see what else could happen, okay? Now this molecule, if we rotate around this bond here, let's reposition the OH pointing to the left, okay, like a Fischer projection. So this is just a bond rotation. This is basically equivalent. It might have different energetics for the different rotamers, but don't worry about that too much. Okay, so we're just rotating around a bond. There's bonds flipping around and whizzing like crazy, right? And now what could happen is we could have protonation from the right-hand side. So here's water, okay? Remember, in aqueous sodium hydroxide, there's no H+, so we're using water as a proton source. So what we want to do here is bring down and protonate the alpha carbon, okay, from the right. So what this is going to do is position the OH pointing to the left now. Okay? So let's carefully look at these two different molecules that we've produced. Here's the curved arrow reaction mechanism for introducing the OH to the left. Here's the curved arrow reaction mechanism for introducing the OH to the right. And here's our starting material. Our starting material has both hydroxyl groups pointing to the right. So it's possible for this molecule to react to give you a certain percentage of this epimer or a certain percentage of this epimer. And again, the ratio or percentage of those isomers is going to be dependent on a lot of factors, including the solvent, the exact type of sugar you have, and you probably need to draw out the chair cyclohexane and examine a lot of stuff. But we're not going to go into that level of detail for sophomore organic chemistry, okay? The fifth reaction I want to talk about today is reduction. If you take a sugar like this, okay, you need to recognize that it's in equilibrium with the open chain form, okay? We talked a lot about that. I keep drawing these arrows backwards. The cyclic form is more stable. but you have small amounts of the open chain form, okay, which you can draw as a Fischer projection, okay. So this is just glucose I've been showing in all of these videos so far. So, and now we know that aldehydes can be reduced with sodium borohydride in a solvent like methanol or water to form an alcohol, okay? So this is the key functional group that's changing here. This carbon right here has the same oxidation state as an aldehyde, okay? So this is your carbonyl, okay? And there it is right there on the top of the chain. So hydride is going to convert that to an alcohol, all right? So that's going to make this structure here. And this is called an alditol. Okay? Where that name came from, I never did research on it, so go figure. Okay, so that's just called an alditol. It's not an aldose, it's not a ketose, it's this thing here. Okay? How does this reaction work? Let me refresh your memory with the reduction of aldehydes with sodium borohydride in protic solvents like methanol or water. I'll do water here. And so that's going to convert this to an alcohol. And I just want to point out the key points here. That carbon is not a stereogenic center because there are not 4 different groups attached. Okay, so you don't need to worry about top attack or bottom attack or something like that. So how does this work? Sodium borohydride is the same thing as just hydride. So I teach my students, just show this hydride attacking here, okay? And that's going to make the alkoxide. And then whatever solvent you have, it's going to be protic. And then that picks up a proton and gives you the primary alcohol. Okay, so aldehydes make primary alcohols. First step is attack, second step is protonation, and that's how this reaction works. Okay? Our 6th reaction is oxidation of monosaccharides. Okay? So the idea here is that you can have an aldehyde at the end of a chain and you can treat that with something and you can oxidize it, okay? And there are 2 different ways that you can oxidize sugar, many different ways actually that you can oxidize sugars, but we're just going to mention a couple of those, okay? So the first thing is with bromine water at neutral pH, okay? Around neutral pH. So pH 6 is slightly acidic, okay? So what we have here is a sugar, and we'll once again draw glucose. Recall again that this substance here is in equilibrium with the open chain form. So let's draw that. So we can see the aldehyde, okay? That's what we're actually going to be oxidizing here. Okay? And how will this appear in an arrow? It's going to look like this. Br2, comma, H2O, pH is equal to 6. And the key functional group here is this aldehyde. You're going to oxidize this aldehyde to a carboxylic acid. It is not going to oxidize any secondary alcohols or primary alcohols in the rest of your sugar, okay? So let's draw this out. And with everything in this chapter, there seems to be a weird name for stuff. This is called an aldonic acid. Okay, that's called an aldonic acid. All right. So how in the world does bromine water at pH 6 oxidize aldehydes to their corresponding carboxylic acids? All right, so the first step is you want to form the hydrate, okay? So this is pH 6, so it's right around neutral. You could do a base catalyzed reaction or an acid catalyzed reaction. I'll do acid catalyzed reaction, okay? So there's a bit of acid in here at pH 6, and all of these steps are equilibrium. I'll just draw arrows from now on, but you're going to form the hydrate eventually. So the first step, you're going to protonate your aldehyde, okay? And you have water present. The water is going to attack this carbonyl carbon, okay, to give you this guy here, okay? So that's attack. And then you have neutral water, water floating around as your general base here. It's going to deprotonate this hydroxyl group, and you're going to form the hydrate, okay? So recall again that aldehydes readily form hydrates because of their stereoelectronic nature, okay? They're sterically available, more available for things to attack it, and they're electronically more deficient, okay? So they're more reactive from a stereoelectronic standpoint. Now that we have this guy here, we're going to attack bromine. Okay, so here's where bromine comes in. Here's bromine, Br2, right? So take one of these oxygen lone pairs and attack bromine. Okay. Okay, and now probably what happens is you deprotonate that proton there, so we'll just use water, okay, as a general kind of acid base that's present in this reaction, okay, and that's going to give me this this guy here, okay. And then what happens is there's going to be an elimination reaction. So I'll just use neutral water here as the strongest base I think that's around. And what's going to happen, so this is the key step. Maybe I'll make this in this arrow in light blue here. This is the key step. You're going to have an E2 elimination basically. Okay, so you're going to eliminate HBr from this molecule here. And what you get is your carboxylic acid. Okay, so you lose HBr. Okay, so that's the elimination step. There's a deprotonation step. Okay, so those are the letters, PA, DA, DE. This is an advanced mechanism, and I'm just showing it here on YouTube in case somebody needs to see it who's taking a graduate level course. All right? All right. We can also oxidize sugars with nitric acid. So we can do an oxidation using bromine water at pH 6, and that's very selective for only the aldehyde. Only the aldehyde gets converted to the carboxylic acid. Our seventh reaction here is going to be oxidation with nitric acid. Okay, let's draw our sugar, and let's show what happens. And this reaction is selective for aldehydes. Okay, here's your aldehyde functional group. And primary alcohols. This is a primary alcohol. It's less sterically hindered, okay? And so, you know, there's of course an excess involved, all right? So if we treat this with HNO3, let me draw then that H, we get a dicarboxylic acid. So on the top carbon, carbon 1, we get our carboxylic acid. These other secondary alcohols, okay, are more hindered. They're less reactive under these reaction conditions and do not react. But the primary alcohol is more sterically accessible, and you get a carboxylic acid here. Okay? As you might guess, this has a special name. It's called an alderic acid. All right. So what exactly is the mechanism by which a primary alcohol can react with nitric acid to give you a carboxylic acid? And what's the mechanism by which an aldehyde can also react with nitric acid to give you a carboxylic acid? Okay. I'm going to show you this advanced curved arrow reaction mechanism, and in case you're taking a graduate class and you just want a seat here in this context. All right? So what you're looking at here is an alcohol that actually gets oxidized with nitric acid to form the aldehyde, and then the aldehyde goes on to make the carboxylic acid. So it turns out that we could just show the mechanism from the alcohol going to the aldehyde going to the carboxylic acid, and that'll take care of all the mechanisms. Okay? Now we want to do what we did in chapter 19 when we did nitration of aromatic rings. We want to make this nitronium ion. So first, we have nitric acid, which has this Lewis structure. Okay? And we want to protonate the oxygen on the right. Okay, so nitric acid is going to pick up takes a while to draw all the pluses and minuses here, so bear with me. All right, so we're going to pick up this proton here. And what that forms is a protonated guy. Okay, plus nitrate. I'm just going to draw NO3 minus as the conjugate base. Now, what happens is water is a good leaving group. Okay, so we want to eliminate water. So this is kind of a key step here. And we saw this again in chapter 19, so this should be review for the advanced student that is interested and good with organic chemistry. So what you get here is the nitronium ion, okay? And you lose water in this step, okay? So now that we have the nitronium ion, we can show how this interacts with an aldehyde, with an alcohol, to eventually give you a carboxylic acid. So let's see how that plays out. Okay. So here's our nitronium ion. And what we want to do here is show first how, so, tuck this in your pocket for now. Let's discuss how a primary alcohol can get converted to an aldehyde, okay? So this guy here is a primary alcohol, okay? And this is going to react, okay, with, I'm going to have it reacting with our nitronium ion, okay? So the lone pairs are going to be your nucleophile that can attack this electrophile, okay? And this is going to form a, well, there needs to be a deprotonation event here, but let me draw out the intermediate. And so let's deprotonate this. Maybe use nitrate, for example, to deprotonate. And that makes, you know, a nitrate ester. So I'm trying to add lone pairs when it's kind of necessary or add something to the value of this. All right, now what we do is we do the same thing we did with the bromination of aldehydes. We do that elimination reaction. So I'll just use water here as a base, and this is going to eliminate, okay, NO2 minus. Okay, so NO3 minus is nitrate that gets converted to NO2 minus, which is nitrite. So this is nitrite being eliminated, and we form the aldehyde. Okay, so here's my primary alcohol getting converted to my aldehyde. We're halfway there. So here's your nitronium ion. Let's draw it in. Here's our aldehyde that we just made through all that laborious drawing of arrows and curved arrows. Now I want to take this and react it with nitrite, for example. So here's nitrite. Okay, and this can attack the carbonyl carbon of the aldehyde to give you this addition product, okay? So let's draw it all out. Okay, my hand's starting to get tired from doing all of this. All right. Now we have this guy here. Now this is in acid, so let's protonate this alkoxide. It looks really uncomfortable to have an alkoxide. In fact, I would probably protonate that first, but I don't want to redo the whole slide. So protonate first. Let's just make a note of this. Protonate first. But here I've already made a mistake, so let me protonate now. So that's going to give me alcohol down here and my nitrate so-called ester up here. Okay, now what we want to do is do the same kind of thing we did with the bromine reacting with aldehydes to give you carboxylic acid. So grab water. And do that nice elimination reaction there. And once again, you're going to lose nitrite ion, and that's going to give you directly the carboxylic acid. Okay, so we've taken the carboxylic acid, the aldehyde, and we've converted it to a carboxylic acid. Okay, so that's the advanced mechanism. In case you're curious, how exactly does nitric acid do that? All right, so the 8th reaction discussed in chapter 24 of the carbohydrate chapter of Klein's book talks about the Kiliani-Fischer synthesis. And this is a chain lengthening process to extend the carbon chain by 1. So if you have an aldopentose, you do this sequence of events, you'll get an aldohexose with 1 additional carbon. And it uses hydrogen cyanide. Okay? So let's look at a review here. Recall that if you have an aldehyde, let's maybe position it like in a sugar. So if you have an aldehyde and you treat this with sodium cyanide with a drop of acetic acid, right? You can make the cyanohydrin. I'm running out of space to draw that triple bond going directly up, so I'll just draw it like CN. And that's a new stereogenic center, okay? And then what we do is we do a sequence of events to transform that to an aldehyde, okay? So that's going to make a sugar. That looks exactly the same. It's got an aldehyde at the top carbon, but it's got that 1 additional carbon in there. And the key detail here is that you form mixtures of epimers, okay? At the C2 position. At carbon 2, we have a stereogenic center that's being born. It used to be the aldehyde, which is trigonal planar and not a stereogenic center. And then the cyanohydrin now has an alpha carbon that's chiral, and the corresponding sugar that's been lengthened is now an aldose with an aldehyde, right? But it has a stereogenic center at carbon 2, so we're going to form epimeric mixtures of sugars here, all right? So I think the reactions here should be kind of familiar, and let me just show you what reagents are used and how this is carried out, okay? So remember, again, your cyclic sugar is in equilibrium with the open form. So I'm just going to start with the open form here. And we'll do a smaller sugar here, might as well. So let's pick an aldehyde with, I don't know, a couple hydroxyl groups, okay? And so the idea here is that we can treat this with HCN. Okay, and then we want to treat this with Lindlar's catalyst. Lindlar's catalyst is palladium with barium sulfate, water, quinoline, and there's a whole bunch of other stuff in there, right? So it's very specially created reaction conditions to get you to the sugars that have 1 additional carbon. Okay, so let's draw in our molecules that are going to be produced. So all of what I'm drawing here on the bottom is from the starting R group or the starting sugar. And then the new carbon that you form could have an OH on the right and a hydrogen on the left. Okay. Almost seems like magic. You're just inserting this carbon right in the middle of the molecule, aren't you? But actually, you're adding it to the top. You're not really inserting it. The other molecule that we could have is the epimer. Okay. None of the other stereogenic centers are altered during this Kiliani-Fischer synthesis. And so the OH could be on the left, okay? So you form 2 different epimers, all right? What's the curved arrow reaction mechanism for this? Well, first you have your aldehyde, okay? And this is going to become protonated either by HCN or a drop of acetic acid or something, okay? Cyanide is going to attack that. Okay, and that's going to give you the cyanohydrin. And this has a new stereogenic center, and it's set at this stage. Now, if we can draw this out a little bit better, the nitrile, remember, has a carbon-nitrogen triple bond. And when we treat this with hydrogen and Lindlar's catalysts, I definitely do not want to even attempt to show you the curved area reaction mechanism for that. I was never good at organometallic chemistry, so I know when not to try something. But what this does is it adds hydrogen across the carbon-nitrogen triple bond, but only once. So you get an H here, and then you get an H over here, okay? So carbon has 4 bonds, nitrogen has 3 bonds, and so that's good. And that's the imine. Okay, I don't know if I'm drawing behind my picture or not, so it's an imine, I-M-I-N-E. And when you add water to this, it's going to, and the Lindlar's catalyst is kind of a basic condition, so it's going to basically hydrolyze this to create your aldehyde, okay? And you lose ammonia in the process, okay? And I don't think it's necessary to show the hydrolysis of imines at this point in the course, okay? So we'll just stop there. All right. All right, now let's talk about chain shortening. This is going to be reaction 9. Okay. Chain shortening is a very valuable technique because you can take glucose and convert it from 6 sugars to 5, then to 4, then to 3, and eventually get down to glyceraldehyde. And that's basically what the Fischer proof is kind of all about. So this is called the Wohl degradation. So these important chemists, they get like 2 seconds of fame in the middle of all of our confusion as we're learning this. So the Wohl degradation shortens the chain by 1 carbons, okay? So let's see an example here. If I've got a sugar that contains my aldehyde here at the top carbon, so this is an aldose once again. And what I'm going to do is add cyanide once again to this, okay? But in a different way. It doesn't look like that, okay? So somehow I convert this aldehyde to a nitrile, okay? So this should put a big question mark in your mind because we're not adding cyanide to it. We're actually replacing the oxygen for a nitrogen, okay? So we're changing that functional group completely. We're not introducing a new carbon. We're changing the carbon of an aldehyde into the carbon of a nitrile. And this, remember, is a cyanohydrin. And this is in equilibrium with an aldehyde at this carbon. So that is in equilibrium with this aldehyde here, okay? So it basically looks like you're taking scissors and snipping it and removing that carbon out of the molecule, okay? So let's take a look at the reaction reagents and so on that are used for this, okay? Let's just choose this sugar here. Okay. First thing you want to do is add hydroxylamine. Hydroxylamine is this molecule here. We talked about it in chapter 19. It's a nitrogen-based nucleophile. It's somewhat toxic too, and this can form your oxime derivative. add in all those H's here. So it adds, it kind of looks like an imine. So this is an oxime. Okay. It's a derivative. So this is called, it's not oxime itself, it's an oxime. It's an example of that. Okay, so this is your oxime functional group. So now what you do is you treat this with acetic anhydride. Maybe I should not draw it like AC2O. Let me draw that out. So we treat this with acetic anhydride. Okay, and this makes the cyanohydrin. One, two, three bonds. Okay, I know it's bent, but no, it's linear, but my drawing is kind of weird. Okay, now that we have the nitrile, we treat this with base, sodium methoxide, for example. And this gives you an aldehyde at that circled portion, okay? And then I've got two OH groups. And I've got my CH2OH here at the bottom. Okay? So a lot of steps there. So let me just show you overall what it looks like. Okay? So this would be step 1. This would be step 2. This would be step 3. Okay? And if you compare the molecules, you'll see that this portion right here has been excised out of the molecule. All right? So let's do an example of this. Let's do threose. Okay. So step 1, we add hydroxylamine. Step 2, we add acetic anhydride. Step 3, we add Naomi. Okay, sodium methoxide. And what that forms is an aldehyde. Okay. With one less carbon. So you're basically taking this portion right here and removing it from your drawing. Okay? Those are all the reactions. So now let me just show you the reaction mechanism for all of those. Okay? So here's our aldehyde. Okay? And when we add NH2OH, nitrogen can attack this guy here to give you the tetrahedral intermediate. Okay, those are all my lone pairs. And now we need to do a series of proton transfers. So it depends on what the solvent is. It might be water or methanol or alcohol or something. But I'll just use something that I'm labeling as a base, okay, to deprotonate here. Whoops, I removed that, didn't I? Now we'll protonate this guy here. So some solvents used here, and that's for the acid-base, general acid-base catalysis. So we'll go ahead and draw our guy there. Okay. Missing a hydrogen and a lone pair. Okay, and then we kick off the leaving group. It could be under basic conditions or acid conditions. I'm not sure really because I don't have much detail on the solvent here, but that's going to give you, and I'll draw the nitrogen pointing up. Kind of the iminium ion looking thing, and then I'll use my base to remove that and get the oxime, okay? Okay, so that right there is the oxime. That's from my starting aldehyde. All right? Now that I have the oxime, what happens next? Let me show you. We treat this with acetic anhydride. Okay? So acetic anhydride is this molecule right here. Okay, and we want to use the lone pairs on oxygen to attack here. And so that C is going to be the tetrahedral intermediate. You're going to have O minus. You're going to have acetate, which will be our eventual leaving group, and you'll have a methyl group there, okay? And there's an H that comes along for the ride here, okay? So at this point, let's just go ahead and kick off our leaving group. So that's an acetate, and the OAC, we've used that abbreviation before, is the leaving group, right? This is a good leaving group. So the theme of this reaction right here on this page is that acetate is a good leaving group. So next what we need to do is do an elimination reaction. Maybe acetate, for example. Acetate here can do an elimination reaction to kick off there. So we'll give you your nitrile, okay? All right, so there's your nitrile. Now, in the last step, what we have is a breakdown of this guy here to give us, and this is with Naomi, to give us an aldehyde having one fewer carbon, okay? So how does this work? Well, the book actually shows this step. I mean, they don't show anything else really. But methoxide is a base, and that can deprotonate here, okay? And this is the tetrahedral intermediate basically, and you can kick off cyanide to give you your aldehyde, okay? And cyanide is your leaving group. So those are the reactions. That's it for this chapter. I hope you jumped around as you needed to look at the reactions and or the synthesis for the 9 different reactions that were covered in this video. That's it for section 6 of this chapter. Thanks for watching. Have a good day.